So welcome everyone to our Introduction to Networks class meeting for the 12th of November. We've got a couple, what I'd call fairly easy, simple modules to go over today. We're going to look at module 13 and then hit on module 14 a little bit. We have made our way up through the network layer of the OSI model, and now we're moving towards the transport layer. Remember that the network layer is the layer that deals with logical addresses. It deals with IPv4, IPv6 addresses. It deals with routing. It deals with path determination. Well, one of the things that we need to be able to do inside of that is determine whether or not a host is reachable. There's a specialized protocol inside of both IPv4 and v6 called the Internet Control Message Protocol. So ICMP, Internet Control Message Protocol. ICMP runs under both v4 and v6. And the best way to think about it is in many ways, it is our troubleshooting, first level troubleshooting tool that we use. So with ICMP, there are different types of messages. For instance, if you've ever pinged a destination and got a host unreachable, that was an ICMP message telling you that it could not get there. And typically what that is your router, your local router telling you that it tried to get to an external host, but it has no route to get there for one reason or another. A time exceeded is when you exceed the hop count. If you remember way back in the annals of your looking at the headers, we actually talked a little bit about them on Tuesday. We talked about the time to live field in an IPv4 or IPv6 header. Once the TTL is at 0, then a TTL time or an ICMP time exceeded will be sent back to the host to tell them that it was beyond the reachability of IPv4 or IPv6. And so that's what we're looking at here. One of the things we can do with ICMP is send an echo request. And that basically is just the ICMP echo request saying, can you get to 30.1? It sends an echo request and expects to get back an echo reply. Now, one of the issues we have in the real world is that because ICMP has been used for nefarious purposes, in other words, it's been used to map networks, it's been used, there's even been a thing called the ping of death. Most of the time, if you try to ping to an external network, it's going to fail. So if I go in here and do a CMD and I do a ping www.google.com, this may work, it may not work, okay? Now that worked for Google, but watch this. If I try to ping www.stanley.edu, which is our web server, you'll notice it fails, okay? Now I can go over to my web browser and I can put in www.stanley.edu, and you'll notice our website is up, even though when I tried to ping it, it failed. The reason for that is most institutions block ping on their external interfaces. So in other words, we don't allow at Stanley Community College, we do not allow the server www.stanley.edu to be pinged inside on our DMZ. Now, Google obviously allows it because they have the ability to mitigate a ping of death or ping sweeps or any of those types of things. So just because you can't ping something on the internet doesn't mean it's totally unreachable, because I can obviously get to our website. But that is the purpose of ICMP, is to send a ping and to find out whether or not something is available locally. Now, one of the things I would do, honestly, let's say I was troubleshooting and I tried to ping stanley.edu and it failed. One of the first things I would do then is an IP config on my machine, find out what my IP address is, and I would try to ping my default gateway, which for me is 254.254. So I would first ping my local default gateway, 192.168.254.254. Works. So I know I can get to my default gateway, and then I would try to ping some other external site besides Stanley. Now this gave me a destination port unreachable, so www.cheese.com wouldn't respond to that. But then I would eventually find out that I could in fact ping Google, which tells me I have access to the internet. It may just be that those host sites are not allowing me to ping them. Internally, however, typically we should be able to ping. So anytime you're on the internal network and you're trying to ping something else internally, unless it's on a DMZ, which I hope everyone knows a DMZ is a demilitarized zone, and it's all part of our border routers that we put our external hosts that typically need to be accessed by internet, have internet reachability is where I put our DMZ. So in this case, there'd be another port off of the router here that would have the DMZ on it. But that's what ping is used for. Ping uses ICMP echo requests and gets back echo replies. Here are some of the different things you can get back with an ICMP message. You can get net unreachable, so the network's unreachable. You can get host unreachable, and these would all be inside of the, if we looked inside of Wireshark at the actual ICMP packet, you would see this as being set in the ICMP options. Protocol unreachable, which means you've tried to go somewhere that maybe www or HTTPS when it didn't support HTTPS, or port unreachable. So you may have tried to go to the SSH port, which is TCP 22 or HTTP 80. And for some reason, HTTP is not running on 80, so that port would be unreachable. ICMP v6 also has many of the same codes. No route to destination. Communication is administratively prohibited. So in other words, it can try to figure out that the firewall is blocking it. 2, beyond the scope of the source address. In other words, it's not available to the source address. Address unreachable, meaning the IP address is not reachable, and the port unreachable, meaning the service is not reachable. We'll learn more about ports as we move into our next module on the transport layer. Do notice that 3 of the different things that are between both ICMP v4 and v6 is they both can return host reachability, destination or service unreachability, and time exceeded. So time exceeded is built into both IPv4 and IPv6. And that's what we're going to look at here, which is every time a packet goes to a router, you decrement the TTL field by 1. Once it reaches 0, then you get a time exceeded. This is important because this means, unlike layer 2, remember frames had no TTL field. So if you get a loop at layer 2, you can actually bounce a frame forever, infinitely. That is impossible at layer 3 in effect because of this TTL field. You cannot have an unlimited loop at layer 3 because the TTL will expire eventually. We do have another tool called Traceroute, and Traceroute allows you to if we can do this. It's TraceRT on Windows boxes. I always get them mixed up. But what this does is sends an ICMP echo request with a TTL of 1, jumps out there, tells me what my first hop is, which you see that's my local gateway. Then it will go to my next hop. And now here's where it gets a little funny though. If they're blocking ICMP messages, I won't be able to get information about the next hop IP address. So I may or may not get the full trace route or the full route to my destination. You'll notice it gives a maximum of 30 hops. So this is only going to try for a TTL of to a limit of 30. After that, it will stop. So we'll let this keep running and see what we get. I'm going to figure that it may show us 2 or 3 of the different hops, and then it's going to stop simply because my ISP is not allowing ICMP echo requests. So Traceroute, while a good tool, again, due to the fact that most of us are blocking ICMP out in the real world, has limited use outside of your network, unfortunately. ICMP v6 has a lot more uses than ICMP v4. One is, man, my phone is blowing up, y'all. Sorry. I have no idea what is going on. I'll put it on. Oh, okay. So we have, remember back when we're looking at our dynamically assigning IP addresses with Slack? Well, that is where ICMP router solicitation messages come into effect. In other words, the router will, or the host will boot up and send out a router solicitation message. And then the router will send back a router advertisement message. And we'll say, depending upon whether, remember, it's set for Slack with stateless DHCP or stateful DHCP, that will be how it responds to tell it how to get its IP address. but that is handled by ICMP version 6, router solicitation, router advertisements. You also can have neighbor solicitation and advertisement messages, which are used for our duplicate detection. So in other words, I can say, okay, I've got this address. I'm going to use this address. Does anybody else have it? And then that way, if it's dynamically creating its host address, it can make sure that it doesn't have a duplicate address. It can also do this when it needs to know the MAC address for a particular IP address. Okay, neighbor solicitation message, which is like an ARP request. The neighbor advertisement is when we're sending an advertisement. Well, whoever has this address, send me your MAC address, and then we get a neighbor advertisement. So solicitation and an advertisement. All handled by ICMP version 6. Here's our router advertisement messages. Again, hi, I am this router. You're going to use Slack to get your global unicast address. Your prefix is this 2001 DBA ACAD :/64. And for your local gateway, use my FE80::1. Use my link local address. All of that is handled by ICMP version 6. So pinging. So there's a couple things we can ping. We can ping our local loopback, by the way. You'll see here, this is stopping because, all right, we did get Windstream. Okay, well, that's good. We got 2 hops. So we now see I'm going up the Windstream. We went to another Windstream. Let's see what we get here. Maybe it will keep going. So we get our entire path. Yep, now we got another Windstream. For some reason I'm having to hit enter to get it to show up, but that's okay. So we got another Windstream. So you can obviously tell I've got a Windstream address. And here's a non-identified address. So I may actually get the full path to it. Let's see if we get our full path. That would be cool if we did. Doesn't usually work that way, unfortunately. Yep, looks like it did. There it is. So there's the full path from my PC to the web server www.google.com, or one of the web servers. There's probably hundreds and hundreds of them. But this is the path, my local gateway here, then to a router at Windstream, to another Windstream, another Windstream, another Windstream, to their final exit, which exits Windstream and goes to this 72 network, and then so on and so forth. This could be very useful if I was trying to track down where my communication was failing, because I could say the last place I could get to was here. So this seems to be an issue between Windstream and their connection to the greater internet, or whatever this happens to be. So that's a pretty neat little thing to be able to do. It's rare that a trace route on the internet actually works. Other uses, we can do ping our loopback 127.0.0.1. This just tells me that, as you see in the picture here, it shows you that the TCP IP protocol is turned on. That's all it tells you. It doesn't tell you there's any IP address there actually assigned statically or dynamically. It's just that it is actually turned on. Likewise, you can ping :/64, I believe that's it. Nope, ping :/0. Let's try that. Nope, I must not have, I have IPv6 turned off. So we'll look at that here in a second. I'll show you I've got it turned off. ::1, sorry, not ::0, ::1. Ping ::1. Yep, so I do have IPv6 turned on and it's working. So this tells me that the V6 protocol is turned on. So if I go in here to control panel, go into my network and sharing, change adapter settings, you will see that I have, under my properties, I have IPv4 enabled and I have IPv6 enabled. And that's what, when I ping 127.0.0.1, that tells me that this is checked and on. And if I ping ::1, that tells me that this is turned on and available. That's all it tells me. It doesn't tell me what the IP addresses are. It just tells me that they are actually up and running. Okay. So that's pinging your loopback. And a lot of times that's our first test in our testing process. We'll ping the loopback. Then we'll ping our default gateway, just like I did. We'll ping default gateway, make sure we can get to our local router. Remember, your default gateway port will always be the closest router port on the same network as you. So here we have the subnet 10.0.0.0/24. This host is using .1 and the router is using 254. And so we would ping and ensure that we could get there. Then typically we ping a remote host. So we try to ping somewhere that's across on the other side of our router. And if that works, then for the most part, you've got full connectivity, okay? Complete and total connectivity. If we don't get this ping, if we ping the remote host and it doesn't work, our next test we could try would be this Traceroute to see where it stops. And we can find out where it stops, and that gives us an idea of where we can begin our troubleshooting process. This is something I use a lot in the classroom when I build out what I call challenge labs. By the way, a lot of times what I will do is I will actually walk into the classroom to give you a classroom best thing once we finally all get back in the classroom. I'll walk in the classroom and I will literally just say, okay, folks, I'll draw on the board. We're going to do this today. We're going to build this network right here. We're going to put a bunch of routers out. We're going to connect them gig 000, gig 000. We're going to connect, and I'll just draw out a network and then give them a series of requirements. All right, so I'll do that, and I'll just draw a network. I'll put a couple of switches out here. So we'll have a switch here. We'll have a switch over here. We'll have another switch. Well, we can't have another switch because we don't have another, but we'll put one over here. Okay. And so now we're going to have switches, and then I'll tell them, you know, hey, we need X number of hosts. Actually, we don't have another one there, so we'll have to use this. Gig 00, because remember, in your classroom, you're only going to have two. You're only going to have two Ethernet ports. But I'd come in here and say, okay, guess what? Down here, we're going to have in this network 200 hosts. 200 hosts down here. Over here, we're going to have 60 hosts. And I'd say, okay, you got the network 172.16.0.0/16, subnet it to make it work here. And then I'll have them build it. And, you know, a lot of times the only suggestions I give them is if there's anything we haven't covered yet. For instance, with this network, since we have not covered routing at all, I would have to tell you how to do your routing, how to set up your default routes on router 0 and router 3, and then how to set up the routes on router 1 and router 2. Down the road, once you get into next semester's content, I wouldn't even tell you that. I'd say, okay, you need to figure out how to do the routing and make the routing work. But these are called what I call challenge labs. But in a challenge lab like this, you could use Traceroute. So I could ping from over here and test. And if I only got to router 2, then I know the issue is probably at router 2, or it could be that I don't have a route back from router 2 or to router 2, depending on how it's set up. But that's where Traceroute is usable in your networking labs themselves. Questions about challenge labs? By the way, one of the things Cisco says, you can add anything into the classes you want. They don't like you removing items from the classes. They do want you to cover all the content, which makes sense because we're trying to get our students to pass the CCNA. But you can add any content you want. That's why I do a lot of challenge labs. And it's one of the big suggestions I give all my instructors is to build and use challenge labs. Questions about that? Well, folks, that's it for ICMP. It's a very simple concept. So let's move over and look at layer 4. Let's look at the transport layer. Let's think about, at this point, we've done framing. So we know how to do framing at layer 2. We know how to do our IP addressing at layer 3. Now we're going up to layer 4, and we're going to look at how devices keep up with multiple communications to different servers and different hosts. We're going to look at how TCP and UDP do this and what some of the characteristics of those two are at the layer. Now, here's an important thing. You get right now on my machine, I have open a web page to Stanley Community College, a web page to NetAcad. I have Zoom open. I have my email open. All of these applications Sorry, y'all. All these applications, I had to have a way to track those sessions between my host and the servers that are providing that communication. That takes place at the transport layer. The transport layer uses a thing called a socket, which is the protocol and port that your communication is based upon or on. At layer 4 with TCP IP, we have two major protocols. They are TCP and UDP. TCP is the reliable, guaranteed layer 4 protocol. All right. UDP is TCP's unreliable little brother, and it does not guarantee delivery. TCP is used for things such as web pages, any type of transactional communication. UDP is used for any type of communication that doesn't require retransmission or would suffer from the retransmission of data, like, for instance, voice over IP. It would make no sense to retransmit part of a voice over IP communication that was dropped due to congestion. So UDP is used for that. Likewise, if you're doing streaming video, UDP is used because we can pixelate. We can drop some of the data and still have our video, but we don't want to try to resend it, because if we do, then we would end up with it out of frame, out of character. So the transport layer tracks individual conversations. So again, here's my PC connected to all these different servers. That is handled by the socket. It handles segmenting and reassembling segments. In other words, we are trying to pull down a large file or web page. That is handled by TCP when it segments each of the different pieces of data into segments or datagrams. It adds your header information. We'll look at that in a minute. And it also identifies the application by using a port and protocol. So for instance, when I tell you TCP port 80, this is a well-known port that is HTTP. What are some other well-known ports? TCP port
22.
22, which is
SSH.
correct. TCP port. This one's a little weird, 20 and 21, because this is FTP. One is for data, one is for control. How about a UDP port?
514 syslog.
Which is one a lot of people don't realize. I run into trouble one time because I had multiple syslog servers running on a machine. I could not figure out why in the world the second one wouldn't start. And finally, I realized that I already had a service running on 514. How about, this is a little bit weird, TCP port 53.
DNS.
This is DNS, and it's typically DNS between servers. So if you're doing zone transfers or server-to-server communication, UDP port 53 is also DNS, but this is typically DNS host queries. So if you're querying like, where is www.cheese.com, that would be using UDP port 53. So these are what are called well-known ports. Yep, go ahead.
The port 53 are used a lot in VMware between the web clients.
Yep.
The host.
Yep. That way it's pulling, it's trying to keep up with the different hosts.
Mm-hmm.
These are known as well-known port numbers, and these are well-known applications. So whenever you see, by the way, the socket would be TCP:80. That would be what we would call that. That would be a TCP connection on port 80. You also will see it sometimes referenced by not only the transport layer information, but the IP header, source and destination IP address, and then the source and destination layer 4 transport information. Okay. POP 3 is TCP 110. Okay. All of these are well-known ports. You can look here. We've got, as we can see here, TCP provides transport layer services for FTP, HTTP, SMTP, and DNS. UDP provides it for DNS and TFTP and other services. That's not the only two it does, but that's two of the main ones that it provides services for trivial file transfer protocol, which is UDP 69. So here we have TCP. This is, remember, the reliable older brother. Okay. So Tim, the reliable older brother, is transmission control protocol. UDP is unreliable. It's a best effort. If, by the way, here's what people don't realize. You can have error correction and checking with UDP, but it happens at the upper layers. In other words, it's going to happen if a protocol like TFTP is used to move a file from one host to another. The error checking would not take place at layer 4. It would take place at the application layer based upon the TFTP application. It could be a checksum at that layer or whatever. UDP itself has no error checking and no way to reassemble segments in the correct order. UDP will put things back together in the correct order because UDP will actually mark segments with a segment number, and then we'll reconnect or recreate the correct packet or datagram on the receiving end. So TCP is connection oriented, UDP is connectionless. Okay, so it just says get it there. We hope it gets there. If it does, it does. If it doesn't, it doesn't. That's what UDP does. That's that unreliable little brother. Now, again, what are they used for? Well, if you need guaranteed reliable delivery, you're going to use TCP. For instance, SMTP, IMAP, any type of email, HTTP or HTTPS connection to a web server, any type of transactional web service, you would use TCP. If you need it to be fast and you need it to be have very little overhead and you don't require acknowledgments and you don't want to resend lost data, then you would use UDP. This is typically voice over IP or any type of streaming protocol, streaming media. Okay, so let's look at TCP in more detail. So TCP establishes what is called a session. It does this with what is known as our three-way handshake. And we'll look at it here in just a minute. I'll show you that. But a three-way handshake is where we do a send, ACK, and an ACK. And the way I explain this to people is, and it's similar to say you're going to go to your in-laws' house, you can go to your mom and dad's house. Before you leave, you call them on the phone and say, Mom and Dad, are you there? Yeah, we're here. Okay, I'm coming over. That's a three-way handshake. I'm establishing that I'm going to go before I ever send anything. TCP does that. It establishes a connection or a full session before it ever starts sending information. TCP also has the ability to do reliable delivery because it actually has acknowledgments. It'll send X amount of information and then expect to see an acknowledgement. TCP provides same order delivery because what it will do is it will mark the segments with sequence numbers and ensure that when they are received, they're reassembled in the correct order. It also supports what is called TCP windowing, which is flow control. So we can actually say, to begin with, we're going to send 2,000 bytes, and then you need to acknowledge it. And then if that works for a while, we can actually go to 3,000 bytes or whatever. It's called a sliding window. And that window allows you to change how much is sent before you have to acknowledge it. Here's a TCP header. You'll see our source port and destination port. And by the way, most source ports on sending host, in other words, those not coming back from a server running an application, the source port's a random number that's picked above, random number picked by the host. The destination port is typically a well-known port of a service, unless it's coming from that service back to a host. Sequence number, acknowledgement number, header length, and then we've got some different control bits here, and we'll learn a little bit about the different control, push, urge, send, fin, reset, all of those that are there. So those are our control bits or our flags we'll talk about a little bit later. But you can see it's a pretty complicated header. Yeah, there's a lot going on here. Here's some of our applications that use it: SMTP, SSH, HTTP. Now let's go look at UDP's header and let's look at the way it looks. Data is reconstructed in the order it's received. Segments are not resent. There's no session establishment. There's no sending or informed about resource availability. It just sends it out there. But take a look at this header. Look at how much simpler that header is. So anything that doesn't have the ability to use or have a lot of overhead, that the overhead would slow it down too much, UDP is the way to go, because this header is very, very simple and takes very little for each individual host or router to process. Here's some of the different applications that use it: DHCP, DNS, SNMP, TFTP, voice over IP, video conferencing. Now notice both TCP and UDP ride on top of IP. So there is a flash flood warning until 5 p.m. in this area. So everybody be careful. So port numbers, here they are. Source port, destination number. Here is what's called a socket pair. So our source port, destination port. So FTP, the source. You'll notice again, this is the client port, which is 1305. The destination port would be port 21 because that's the FTP well-known port. This is the web client. So in other words, if this PC right here on the left, the source of 1.5, was connecting to two different applications or two different services on the server, it would have two separate TCP sockets. It would have one that would be TCP, and this is the source port 1305 that is randomly chosen by the source, going to the well-known port of 21 because it's going to the FTP service. Likewise, it would open a web browser. It would pick a random port of 1099. So this would be TCP 1099 going to the destination port of port 80. This is how 192.168.1.5 keeps up with its FTP connection to this server and its web connection to this server 1.7. Likewise, this is how 1.7 keeps up with what information should go to the correct application on the source 1.5. Because when it sends things back, it simply reverses the source and destination IP addresses, and it reverses the source and destination port when it responds to the source request. Does that make sense to everybody? See how we're getting everything put together, by the way, now? Here's our MAC address. So here's our framing. Here's our layer 3 addressing, which is our IP addresses. And then here's our layer 4 protocols and ports. And then finally, in this user data, by the way, this user data would be our application layer information, that whatever's being taken care of by the application. Maybe it's a request for a file, maybe it's a request for a web page, whatever. All of that's carried inside of the application layer information that is user data here. And then this trailer would be the frame trailer that would be part of the frame that was sent. To me, this is amazing that we ever get anything to work. I mean, think about it. When I go out here and click here, and I go to ASC ITC, okay, and I go to my instructor training center, I'm going to show you our class schedule. I don't have our new class schedule coming yet, folks, but I will have it soon. And we will have all 3 of the CCNA classes, and they'll begin probably 1st of February. It's when we'll begin our next set of classes. But to think that every time I click to move to one of these, an entire series of packets were being created, they were being packaged, they were being encapsulated, they were being sent to my default gateway. And that response was coming back from Stanley Community College, which is pretty close to me here, but still absolutely amazing. I mean, that is really kind of amazing that we're able to have this type of communication so quickly around the world. Okay. So here's our well-known ports, 0 to 1023. Registered ports are 1024 to 4199, 49151. So some of these can be registered for applications, some are not. And then above that, these are typically used for dynamic ports. So we do typically see in our, when we do Wireshark captures, that the source ports are 49,152 and above. Here's some of those well-known port numbers. Okay. Again, 20 and 21 for FTP because data and control. 22, 53. I wouldn't remember all of these. I would just have a good understanding of, the well-known ones. A lot of HTTP 80 and 443 you need to know. Sometimes you'll see POP3, 110, TCP 110, and 143. Anybody know the difference between POP3 and IMAP, the major difference as far as for protocols for receiving your messages? These are both protocols for downloading emails off of an email server. And typically this POP pulls all your mail down locally to your mailbox and does not leave a copy. Now there are ways in POP3 to in most clients to say to leave a copy up there, but that's typically what it's designed for. IMAP has a lot more options to allow you to leave it on the server and just read it, not pull it down to a local mailbox. So now watch this. This is pretty cool. So if I do a netstat command, I can spell it. You'll see all of the different sites that my machine has a connection to. Okay, so these are the different protocols. It's a good idea sometimes, by the way. I'm connected to something with HTTPS. That looks like Elastic. That's something in Amazon. That's probably this actual page right here where I'm connected for Netacad. But it's a good idea sometimes to run netstat on your machine and just look and see what's connected to what, so you can figure out who's connected what and where, and if any applications that you may not be aware of are actually out there doing things. Okay, so that's what netstat does. Netstat shows you your connections. You can also use the option Control-C if you want to break out. Just Control-C, -N. It'll show you all the different active connections, whether or not they're closed, wait, established. Established means I've done a three-way handshake and I have connectivity there. So I've got a couple websites here that I've got HTTPS connections to. So good idea to run that on your machine and check to see what's going on your machine. So how does TCP work? Well, let's imagine I want to establish a TCP connection. What I'm going to do is I'm going to first send a SYN with a sequence number attached to it. So I send a SYN, and by the way, that's one of the different options inside of TCP. There's push, urge, send, fin, reset, and I always forget the last one. Somebody help me out here. So it's TCP, you got push,
reset,
reset. That's it. Push, fin, reset, urge, send, ACK, and that's it. That's the 6 right there. Push, fin, reset, urge, send, ACK. Those are the different items you can have inside of your TCP settings. When I want to establish a connection, I send a SYN. Okay, it goes over to B. B will then send back a SYN-ACK. In other words, it takes my sequence number, I sent it, adds 1 to it, so that's the acknowledgement, and then sends its sequence number back to host A. Host A will then send an ACK, and at this point, we have a full established connection. So it'll say established. Until this happens, we have what's called a half open connection. In fact, there used to be, and still is, you can do what's called a SYN flood. You can take and send thousands of SYNs from a spoofed set of addresses and flood the half open connection on a server. Most firewalls now can see that and will block it. But once this happens, we now know that we can start sending information between A and B because we've established our connection. Again, the example is you call your mom and dad, hey, are y'all at home? Yeah, we're here. Okay, I'm gonna come over and see you. So you called them, they acknowledged they were home, and then you go see them. Likewise, TCP has the ability to do session termination. In other words, it can send a fin and say, hey, we're done sending things, so I'm gonna send you a fin. Host B will ACK it, and then send another fin and say, okay, and then it will, host A will ACK it, and then it will actually tear down that connection. This is what I call the correct way to do a relationship breakup. In other words, you call a person and you break up with them. There is another way terminate a session with TCP, and that's by just sending a reset. And that's when you break up with somebody by text or something. So just kind of a little example I give my students. But your three-way handshake, that's the control bits we talked about here. Push, urge, act, push, reset, send, and fin. Those are those control bits that are part of the connection establishment, termination, and the connection control of TCP. And there's a video I'll let you watch yourself so you can do that. So how do we get reliability and ordered delivery? Well, delivery, one is segment numbers or sequence numbers. We put sequences or segments have sequence numbers on them. So when they're received, you can put them back in the correct order. That's how it really happens. Okay. The other way we can do it is we do have the ability to do retransmissions. In other words, if I send multiple segments with sequence numbers and I go and act, I say, okay, I did not get these four, or these 2, 3, and 4 never showed up. So B will say, oh, act 3 and say, I got up to, 3, but I didn't get that. And then so A will then resend 3 down and they'll act it. Now you do end up with duplicate segments, but TCP is able to see those duplicate segments and throw those away. There's another way to do this though, is it can actually act individual items. So in other words, instead of just acting 3 and then having to resend everything, it can say, hey, I'm gonna act 3 and 5 through 10. So I got up to 2 and I got 5 through 10. So you only need to send me 3 and 4 and anything after 10. So this gives you the ability to act, called selective acknowledgement, or SAC. So you're not gonna act just the last one you saw. You're gonna act acknowledge a group of segments that you saw. Now, the window size is how much you send before you actually will do acknowledgements. And the window size, this used to be a huge issue. And in fact, for those of you who've been working in IT as long as I have, Windows 95 had a initial window size that was extremely small when they put it out into the wild. And it caused a lot of issues with the performance of TCP/IP on Windows 95. Many of us went in and made registry changes to our PCs to increase that window size to make it more efficient. The window size does change based upon negotiations. So in other words, during the three-way handshake, we'll agree upon a window size. If that window size continues to work well, then there's a possibility that the window size can go up. If we start seeing a lot of drop segments, then the window size can go down. That's called a sliding window that is available. So that's what we're talking about, the sliding window here. So it's a continual adjustment, can go up or down, depending upon if segments are being lost. But there is, by the way, a maximum segment size, and that typically is based upon the protocol you're running at layer 2, so your frame. And we see here it's 1460, and that depends completely upon your particular frame size. Could have jumbo frames. If you have jumbo frames, then it could be above 1460. It just depends on your layer 2 frame size. Okay. In this case, I've done 1460 because they subtracted the IP and TCP headers from the maximum transmission unit of Ethernet, which is 1500. They subtracted the 20 bytes of the IPv4 header plus the 20 bytes of the TCP header to get a maximum segment size of 1460. Sometimes you will, especially if you stay in networking long enough, we have to play with segment sizes occasionally when we're running VPN tunnels and those types of things, because VPN tunnels can add additional headers on top of our segments, and we may have to play with the segment sizes sometimes when we do that. Again, congestion control, this is looking at how we can change the window size and change our acknowledgement sizes. Okay, sorry for the phone, but we're working at home. Y'all know how it is. So UDP, low overhead, no reliability unless it's built in at the application layer. So we don't care whether or not it can get there or how it gets there. It just gets delivered with UDP. So again, we don't have any session control. We just use our well-known ports and a dynamically assigned or created port on the host, and that's it. I mean, that's basically how UDP works. And if we do need, again, error checking, or we need to be able to guarantee anything about a UDP connection, it has to take place at the application layer. Now, folks, that's it. That's all I have for ICMP and TCP UDP. Are there any questions about those two modules? Any questions? Watch the videos. Let me know if there aren't any questions. You can see we're doing pretty good. We're actually pretty close to getting into the last 3 chapters, the application layer, which we'll talk about next week, and we'll talk about the network security fundamentals and building a small network, folks. And then we will be on our way to getting you ready to take the Handson Final, which is just another lab in NetLabs. By the way, I'll show you real quick. Our Handson Final will be, you'll go in here and you will simply make yourself a reservation in our class. So you'll go into our fall class, and this is the Handson Final, this skills assessment. You'll click here, and then you will make a reservation for yourself, and this will be the skills assessment. So you just do it like any other lab. I would give myself 4 hours. I would go ahead and give myself full 4 hours. You're not going to need it, but I would do that, and then I will show you kind of just give you a sneak peek here. So that way, if anybody watches all the way to the end of today's class, they'll get a sneak peek of what the Handson Final looks like. So we'll let that keep going. Any questions while that's booting up?
Just want to bring up a point about NetStat. They're phasing it out on Linux. The new command is SS. And SS shows IPv6 as well.
Okay, what was it again? Say it's S.
Just SS.
SS?
On Linux.
On Linux, okay. I wonder if they'll do that on, let me look at this. Linux SS command. Oh, socket statistics. Okay, well, makes sense to call it SS. Let's see something. Windows. Maybe they'll have it eventually on Windows. But okay, so in Linux now it's called SS.
Exactly.
That's cool. That's very cool. Thank you. That's it makes sense. I mean, socket status, because these are sockets. Anything the IP address plus the port number is the socket.
Do you think I'm still a little stuck on ICV6 a little bit, so you don't have to do it today, but that may be something I'll get up with you sometime about going over that again, because again, it's still a little new to me.
That's fine. No problem at all. We can definitely do that. Just real quick, here's the topology you're going to have for your Handson. So you'll see it's pretty simple configuration of router, switch, 2 PCs. Just real quick here too, you'll see that you're going to have to develop an IP addressing scheme. You're going to have to configure security settings and IP address settings, verify end-to-end connectivity, and then just gather some information. So it's a pretty simple test. I think by the time you get through the 17th module, you will be very well prepared to do this. But we will also have the ability for you to practice before you actually have to do the hands-on. But the hands-on will be done inside of NetLabs, and I grade it by looking at your all the commands that you've typed in inside of NetLabs. I do have the ability, as you know, to see everything you've typed in. So just wanted to show you that. So this skills assessment is our hands-on test. So anytime I talk about the hands-on test, it's the skills assessment inside of NetLabs. And if it shows up in the class as your assignment, when you look down here and you see, let's see where it's at down here. It's way down here. The skills exam, this skills exam hands-on, this is that skills assessment that you will do inside of your inside of NetLabs. In fact, I'm going to move this up here because that's just the practice. So there's a practice one that you can do inside of packet tracer. So, and Ken, were you talking about ICMP version 6 or just IPv6?
IPv6. I
Okay.
mean, I can send you something a little bit later. Maybe if you have time, you can get together with me.
Please do. Yeah, and we'll definitely we'll schedule a meeting with just the two of us, and we can do that. So.
Okay, cool. Thank you, sir.
Yes, sir. Okay, everybody. Well, that's all I have for today. So I hope you have a great afternoon. And like I said, please don't cross any moving water, and everybody stay safe.
All right. Thank you, Kelly.
All right.
Thank
Take care,
Thank you.
everybody. Bye-bye.
Bye.